In the last few classes, we have formulated the necessary mathematics required for applying variational method in quantum mechanics. Now we will move to the applications. Rather than applications, I must tell you some formal examples where we will find how variational method can be applied in quantum mechanics. As such, as per the demand of our syllabus, we will have to talk about only, I think, helium atom. Anyway, we will do 2 or 3 examples. First of all, we will begin with the variational method being applied to linear harmonic oscillator. Linear harmonic oscillator is rather a known system, as you all might know. You have started talking about this even in your degree classes, and you have done it 2 or 3 times as the applications of quantum dynamics and even in the time independent perturbation theory. Again, we will apply variational method to this formal problem in quantum mechanics, that is linear harmonic oscillator, which is a system that is performing a dynamics under a potential equal to say half kx square, to which it is subjected, or a quadratic potential in terms of the instantaneous displacement to which it is being subjected. Now, in the language of variational method, to apply the procedure to this particular problem, we'll have to first of all identify a trial wave function, a most suitable wave function that we have formulated on the basis of some educated guess, taking into consideration the physical inductions of the problem. Let me do this exercise for the ground state of the harmonic oscillator. In the ground state, the harmonic oscillator wave function is smooth everywhere. It is represented by an even function and it vanishes. This is in fact a quality of all well-behaved wave functions. This wave function should tends to 0, or that must vanish as x tends to plus or minus infinity. This never means that this is equal to 0. This should tends to 0. This must vanish as x tends to plus or minus infinity. All these properties are satisfied by a mathematical function which is nothing other than a Gaussian wave function. Gaussian is represented, as you know, by the equation psi 0 of alpha comma x, where x is the instantaneous displacement of the harmonic oscillator and alpha is an adjustable parameter. I'll tell you what alpha physically means very shortly. That's equal to a, where a is introduced as a normalization constant, so that in the Rayleigh-Ritz formula, I will be taking the denominator as a unity once I evaluate this normalization constant in the beginning itself, e raised to minus alpha x square, where alpha is the adjustable parameter. That make one Gaussian different from the other. So for example, suppose you have a Gaussian function like this, another Gaussian function say like this, this is somewhat thin. These are differing in terms of this width or separation between the 2 arms of the Gaussian. Generally, this is characterized in terms of a parameter referred to as the full width at half maximum, FWH. See, this is the maximum amplitude or intensity point of the Gaussian, and this is supposed to be the half maximum intensity or amplitude. And there will be definitely 2 symmetrical points having this half maximum intensity. The separation between this half maximum intensity is nothing other than the full width at half maximum, as this name indicates. And this is being represented as a alpha. For this Gaussian, alpha will be different from this kind of a Gaussian. And I'm not sure whether this full width at half maximum or this separation has any deciding role on the Gaussian wave function representing the linear harmonic oscillator. So to cope with this idea, I take this as an adjustable parameter and I introduce this as a alpha. Of course, it is in this in terms of this parameter alpha, I'll be evaluating first of all the ground state energy. Then we will have to apply the variational principle that will give me an exact value of alpha. Upon substitution of this value of alpha, the expression for the energy, which is nothing other than the expectation value of the Hamiltonian, and in this expression, I'll be getting respectively the energy eigenvalue of the oscillator in the ground state and this wave function in an exact manner. So I have introduced this normalization constant, so it's my duty to evaluate this normalization constant first of all. For normalization, scalar product of this wave function with itself should be equal to 1, or mathematically integral from minus infinity to infinity psi star psi, that is nothing other than the square of this one, because this is not purely a complex function. So a square e raised to minus alpha x square into e raised to minus alpha x square, make it e raised to minus 2 alpha x square dx equal to 1. Now I will be making use of this standard integral every here and then whenever I am going to cope with this linear harmonic oscillator problem. It is integral from minus infinity to infinity x power 2n e raised to minus a x square, where a is the coefficient of minus x square in the power of the exponent term. That's equal to square root pi by a. Take care of this a. It will be doubled on the other end of this formula into 1 into 3 into 5 etc. up to 2n minus 1, where 2n is the power of the x term in the integrand. So this is the product of the odd integer terms. That is why I am not going to write it as a 2n minus 1 factorial. I can write it in that manner once I tell you that it is all these odd integers divided by twice the coefficient of minus x square in the exponent term whole raised to n, where n is half of the power of the x term in the integral. So I will be making use of this formula. Here x term has a power that is 0, which is again even. So a square normalization constant taken out of the integral into root pi by a, square root pi by, instead of a I have 2 alpha here, that is the coefficient of minus x square in the exponent term, into 1 into 3 into 5, there is say 2n equal to 0 itself, so there will be only 1 as the term, divided by 2a power 0, so that term will not be there in this expression, that's equal to 1, which make a to be equal to 2 alpha by pi raised to 1 by 4. So the normalization part is over. Once I have met with this in the beginning itself, I can remove the denominator term in the Rayleigh-Ritz variational formula. So the first term is over, or first step of applying variational method is over. Now we move on to the second step. We will have to evaluate the energy eigenvalue as the expectation value of the Hamiltonian. As you know, Hamiltonian of the harmonic oscillator is kinetic energy plus potential energy. Kinetic energy as usual is minus h bar square by 2m d square by dx square, since it's a one-dimensional problem, plus potential energy, we replace the spring constant of the oscillator by m omega square, then potential energy become half m omega square x square. So I'll have to evaluate in the scalar product psi 0, h psi 0, where psi 0 is given by this expression. That's equal to integral from minus infinity to infinity. I must apologize you, I have omitted minus infinity limits of the integral. A e raised to minus alpha x square, and h is substituted. Apologies again for putting all these steps in the expression. Into psi 0 in the ket space, that is a e raised to minus alpha x square. Now I'll have to account for the operation of these two operators upon the vector in the ket space. Then this will be splitted into two different integral terms. A square integral minus infinity to infinity minus h bar square by 2m constant e raised to minus alpha x square d square by dx square of e raised to minus alpha x square dx, plus again a square integral minus infinity to infinity, m omega square by 2 is also constant. Okay, I take it out of the integral in the next step. e raised to minus alpha x square into x square into e raised to minus alpha x square. I need not account for any commutation because it's simply x square, so I can multiply e raised to minus alpha x square with e raised to minus alpha x square. Make it say x square e raised to minus 2 alpha x square. Now we have to evaluate these two integrals separately. For that, first of all, in this term, I'll have to account for the second derivative of e raised to minus alpha x square. That itself make two different terms for me. So let me decompose this as the sum of two terms, term 1 this one and term 2 this one. Term 1 is minus h bar square by 2m a square integral minus infinity to infinity e raised to minus alpha x square, second derivative of e raised to minus alpha x square. That is, these terms are repeated. D by dx of e raised to minus alpha x square, d by dx of first derivative of this one. First derivative is written in this bracket, derivative of e raised to minus alpha x square, e raised to minus alpha x square into derivative of this function of function, minus alpha x square has a derivative minus 2 alpha x dx. Now again this is to be differentiated using the product rule of differentiation. These terms are repeated. First function e raised to minus alpha x square into derivative of minus 2 alpha x minus 2 alpha plus second function minus 2 alpha x is there into derivative of this one. That is derivative of exponent e raised to minus alpha x square into derivative of minus alpha x square, that is minus 2 alpha x. Once it is multiplied with this first term minus 2 alpha x, make it say 4 alpha square x square. That is minus h bar square a square by 2m integral minus infinity to infinity. This is the positive term. Let it be written first. 4 alpha square x square e raised to minus 2 alpha x square minus 2 alpha e raised to minus 2 alpha x square dx. Let me integrate it after evaluating or simplifying the second term, because that term also must give me an x square e raised to minus 2 alpha x square term. So I can combine those two terms so that the number of steps that are to be integrated could be reduced. Now the second term is a square m omega square by 2. As I said, these are the constants. Integral minus infinity to infinity x square e raised to minus 2 alpha x square. This term also contains this integral minus infinity to infinity x square e raised to minus 2 alpha x square dx. So we combine these two terms T1 and T2 to reduce the ground state energy in terms of alpha as a square m omega square by 2 integral minus infinity to infinity x square e raised to minus 2 alpha x square dx, the potential energy term, and these two terms minus h bar square a square by 2m, this one that is written here, minus h bar square a square by 2m into minus 2 alpha e raised to minus 2 alpha x square, make it say plus. Now this integral minus infinity to infinity quadratic x term could be taken out and combine these two terms so that the total number of terms for integration will be reduced to 2. That is a square by 2 into m omega square minus h bar square by m for alpha square integral minus infinity to infinity x square e raised to minus 2 alpha x square dx plus h bar square by m a square alpha integral minus infinity to infinity e raised to minus 2 alpha x square dx. That is a square by 2 into these terms are repeated. This integral, that is root pi by 2 alpha into 1 into 2 into up to 2n minus 1. 2n itself is 2, then there will be only 1 divided by 2a. Instead of a, I have 2 alpha, then 2a will be 4 alpha raised to n. N is half of the coefficient, half of the power of x in the integral, that is 1 itself. Plus, and for this h bar square a square by m into alpha, this I have done in the normalization step, this square root pi by 2 alpha. So root pi by 2 alpha is common for these two terms. A square is also common. So a square root pi by 2 alpha is taken out. What remains is m omega square. Yeah. Here let me open this bracket. M omega square divided by 2 into 4 alpha make it 8 alpha minus 4 h bar square alpha square by m. 4 alpha is there, so 4 vanishes, only 2 will be there, 1 by 2. H bar square alpha also goes, alpha divided by m. So we open this bracket with a square by 2. A square is taken out. Root pi by 2 alpha is also taken out, and we open this bracket by 2. Make it say a square by into root pi by 2 alpha into m omega square by 4 alpha into 2, make it 8 alpha minus 4 vanishes, there will be only half h bar square alpha square divided by m. So these terms repeated, plus root pi by 2 alpha is taken out. What remains is h bar square a square alpha by m. Make it say h bar square alpha divided by m. A square is already taken out. Now a square is nothing other than 2 alpha by pi. As we have seen earlier, a equal to 2 alpha by pi raised to 1 by 4. So a square will be vanishing with this term root pi by 2 alpha. And we obtain the ground state energy of the harmonic oscillator in terms of alpha as m omega square by 8 alpha plus h bar square alpha divided by 2m. And this is the end of this step number 2. Now we have to apply the third step, that is the application of the extremum condition. For I must rather tell you minimization. For maxima or minima, the mathematical condition is derivative of this quantity with respect to the independent variable alpha should vanish. Then derivative of this one is m omega square by 8 into derivative of 1 by alpha minus 1 by alpha square plus h bar square by 2m into derivative of alpha with respect to alpha is 1. That's equal to 0. Take this negative term to the right side. Make it say m omega square by 8 alpha square equal to h bar square by 2m. Now 8 and 2 will be vanishing to make it say 4. I require alpha. Alpha square is then equal to take these terms on the right side, h bar square by m to the left side. M square omega square divided by 4 h bar square. Then alpha will be, all these terms are square terms. You can omit these squares. Alpha equal to m omega divided by root 4, that is 2h cross. So we have evaluated alpha explicitly in terms of the parameters related to the harmonic oscillator. Once we have evaluated alpha, in the fourth step we substitute this value of alpha in the expression for the ground state energy in terms of alpha, that is m omega square by 8 alpha plus h bar square alpha by 2m. Substitute alpha equal to m omega divided by 2h cross. Then this becomes m omega square by 8 into m omega by 2h cross. 8 and 2 will be crossing. Plus h bar square by 2m into alpha, that is m omega by 2h cross. This make m vanishes, omega cancel with 1 omega in the numerator, h cross come to the numerator, 4 is there in the denominator. 1 by 4 h cross omega, plus here also m vanishes, 1 h cross will be vanishing, 1 by 2 into 2 make it 4 h cross omega, that is half h cross omega. This is 2 times 1 by 4 h cross omega, make it say half h cross omega. And this is exactly the ground state energy of harmonic oscillator, quantum harmonic oscillator, or the 0 point energy of the quantum harmonic oscillator, that is evaluated very accurately applying the variational method. And we substitute the value of alpha in the expression for the normalized wave function psi 0 equal to normalization constant 2 alpha by pi raised to 1 by 4 e raised to minus alpha x square. Alpha is substituted m omega by 2h cross, then this becomes 2 by pi m omega by 2h cross, 2 will be crossing, raised to 1 by 4 e raised to minus m omega by 2h cross x square. That is m omega by pi h cross raised to 1 by 4 e raised to, this half is written as a coefficient for this term, m omega by h cross x square. Now this is exactly in the mathematical format of a Gaussian, that is e raised to minus half alpha x square, or e raised to minus half, there will be a constant term, into square of this independent variable, say x square. So this somewhat exactly represent the ground state wave function for the linear harmonic oscillator. Often precisely we represent this in terms of the Hermite polynomial, and this is complementing the exact expression for the ground state wave function represented by the Hermite polynomial. So this is about the application of variational method to linear harmonic oscillator problem in the ground state. Then I have told you that the variational method could be applied to the excited state as well. Yeah, we will check this variational method or validity of variational method for the excited state of linear harmonic oscillator. Variational method, linear harmonic oscillator, first excited state. So the first step, we will have to identify the most suitable trial wave function. In the first excited state, this wave function should be odd. Even I can go with this single idea. I already have a ground state wave function which is an even function represented by the Gaussian. I simply have to multiply that term using an odd function, say x. That itself may give me a very suitable wave function, or x cube can also do well. Anyway, we will do it say in terms of x. Another quality, this must vanish as x tends to plus or minus infinity. A Gaussian will do that precisely, and it has one node in the first excited state. This also, that is something I get from the physical intuition about the problem. And for the last but the most important, this wave function must be orthogonal to the ground state wave function. Scalar product of this wave function psi1 with psi0 must vanish. For that, this needed to be an odd function that itself mathematically gave me this condition being satisfied. So let me take this wave function as a x into e raised to minus alpha x square. Here also I intend to, or I would like to normalize it using a different normalization constant, say beta, or say b. For the time being I have written it's a b. Now normalization necessitates scalar product psi1 equal to 1, that is b square x square e raised to minus 2 alpha x square dx being integrated from minus infinity to infinity should be equal to 1. That is b square, again we apply the formula root pi by 2 alpha, 2n is 2 itself, so 1 divided by 2a, that is 4 alpha, equal to 1. Or b equal to, I have a mathematical simplification here. I can square this and put it inside the square root term. So in the numerator I will have pi square divided by, in the denominator there will be 2 alpha into square of 4 alpha. That is 16 alpha square. Make it say 2 into 16, 32 alpha square into alpha cube. Take these terms to the right side so that I'll have to just take the reciprocal. Square root of 32 alpha cube divided by pi, so that b equal to square root of the square root term, that make the power as a 1 by 4. So the normalization constant here is 32 alpha cube by pi raised to 1 by 4. Take care of this term. In the integral there will be b or b square, something like that coming out, that is to vanish with the reciprocal of this term. So the first step is over. Now the second step, we will have to evaluate the energy eigenvalue of the relevant quantum state in terms of this parameter, say alpha, which is the adjustable parameter. Scalar product psi1 minus h bar square by 2m d square by dx square m omega square x square by 2 psi1. We substitute these terms and separate this into two different integrand terms. Integral minus infinity to infinity psi1 bx e raised to minus alpha x square, Hamiltonian bx e raised to minus alpha x square. Now there will be two different terms, this one and this one. That is b square taken out, integral minus infinity to infinity minus h bar square by 2m x e raised to minus alpha x square d by dx of e raised to minus alpha x e raised to minus alpha x square plus m omega square by 2 integral minus infinity to, I meant it's a d square by dx square here. D square by dx square. Sorry for putting these two here. M omega square by 2 integral minus infinity to infinity x e raised to minus alpha x square x e raised to minus alpha x square dx. Of course, we will now evaluate d square by dx square of x e raised to minus alpha x square. That is d by dx of first derivative, first function x into derivative of e raised to minus alpha x square, e raised to minus alpha x square into minus 2 alpha x plus e raised to minus alpha x square into derivative of x, that is 1. Now d by dx of this one, this is a positive term, e raised to minus alpha x square minus 2 alpha x square e raised to minus alpha x square. This term is rearranged. Again, we have two different terms here that are to be differentiated. Derivative of e raised to minus alpha x square, the first term that is written here. Minus 2 alpha is constant. Now we will have to apply the product rule of differentiation here. X square into derivative of e raised to minus alpha x square, repeated. Plus second function e raised to minus alpha x square into derivative of x square, that is 2x. That make it say minus 2 alpha x e raised to minus alpha x square. Minus 2 alpha x e raised to minus alpha x square. This bracket is opened, minus 2 alpha, make it 4 alpha square, x square into x cube e raised to minus alpha x square. Again minus 2 alpha into 2x, that is minus 4 alpha x e raised to minus alpha x square. That is equal to, there are two terms containing x and one term containing x cube. Term containing x cube is 4 alpha square x cube e raised to minus alpha x square, and these two terms are combined, minus 2 alpha x e raised to minus alpha x square minus 4 alpha x e raised to minus alpha x square, make it minus 6 alpha x e raised to minus alpha x square. Then the integral to be evaluated, E1 of alpha equal to b square minus h bar square by 2m is taken out from the first term. Integral minus infinity to infinity x e raised to minus alpha x square, these terms repeated. X e raised to minus alpha x square is to be multiplied with this term, plus the potential energy term b square by 2m omega square integral minus infinity to infinity x raised to 4 e raised to minus 2 alpha x square dx. These terms can be simply multiplied because the operator domain has only mathematical function x square into x make it x power 4 e raised to minus alpha x square into e raised to minus alpha x square, make exponent minus 2 alpha x square dx. That is minus h bar square b square by 2m. Yeah, we will combine. This term contain x into x cube, that is x power 4. And this term also contain x power 4. We can combine these two terms. And for this term, there will be minus 6 alpha x into x, make it minus 6 alpha x square e raised to minus 2 alpha x square. So open this bracket. Along with that, combine the term containing similar powers of x raised to 4 for similar integral terms, integral minus infinity to infinity x raised to 4 e raised to minus 2 alpha x square dx. Yeah, these steps are repeated here. Opened and bracket in the first term is opened. Now we will have to combine them. Terms containing similar integrals. One integral is this one and the other one is this one. So in this term and this term, this x power 4 term is there. B square by 2 is common for both of them, that are taken out. And for this term, that is m omega square remains. Minus for this term, b square by 2 is already taken out. Minus h bar square by m is there. Into 4 alpha square. Minus 4 h bar square alpha square divided by m. Into common integral is integral minus infinity to infinity x raised to 4 e raised to minus 2 alpha x square dx. Plus this term, minus into minus make it plus 2 and 6 make the number 3. H bar square b square by m into alpha. H bar square b square alpha by m, integral minus infinity to infinity x square e raised to minus 2 alpha x square dx. Now we apply the result again. These terms are repeated. Root pi by 2 alpha, 1 into 3 divided by 4 alpha power 2, because 2n is 4 here, so n is 2. And 2a term is twice 2 alpha, that is 4 alpha. Plus this term becomes, this coefficient is repeated here. This we have already evaluated 2 or 3 times, root pi by 2 alpha. So root pi by 2 alpha into 1 by 4 alpha. I think this is nothing other than the reciprocal of b square term. So let me take this as common from these two terms. Root pi by 2 alpha into 1 by 4 alpha is square root of pi by 32 alpha cube. That is taken out. B square into root pi by 32 alpha cube into 2. I have additional here, so I'll open this with this bracket. M omega square by 2 into root pi by 2 alpha into 1 by 4 alpha is taken out. What remains is 3 by 4 alpha. 3 by 4 alpha is written here. Minus 4 by 2. Yeah, 2 will be crossing very shortly. Yeah, I think I have put it for 4 to be cancelled with 4 here. So 4 by 2 h cross square alpha square by m into 3 divided by 4 alpha. Plus, and for this term 3h bar square, b square is taken out again for this term also, alpha divided by m. And this is nothing other than, say, reciprocal of b square. So b square will be vanishing with this. What remains is 3m omega square by 2 into 4, 8 alpha, minus 4 will be vanishing, 3 by 2 alpha also will be going here. Alpha is there, alpha square is there, and that will go with this alpha. Then this is for all goes 3 by 2 h cross square alpha divided by m plus 3 h cross square alpha divided by m. Yeah, clearly these two terms could be summed up as these have alpha in the numerator. 3m omega square by 8 alpha, 3 by 2 h cross square alpha by m with a minus sign plus 3 h cross square alpha by m. 3 h cross square alpha by m is common. Then 3 h cross square alpha by m into 1 minus half, that is plus half. So this becomes 3 by 2 h cross square alpha divided by m. So we have evaluated the energy in terms of the parameter alpha, that is step number 2 as long as variational principle is concerned. Now we will have to account for the minimization of this energy with respect to alpha. For that, dou E1 of alpha by dou alpha equal to 0. Derivative, we take it, say, first term has, actually this is the second term that has only alpha in the numerator. So derivative of alpha with respect to alpha make this to remain this coefficient term. And for the first term, there was alpha in the denominator. That has a derivative minus 1 by alpha square, and these coefficients are repeated. That's equal to 0. Equate them. 3m omega square, yeah, 3 will be vanishing with 3, and 2 and 8 also will be vanishing. To make it, say, m omega square 8, I have repeated 8 alpha square equal to h cross square by 2m. For alpha square equal to 8 and 2, make it, say, 4. M square omega square divided by h cross square. Again, we obtain alpha equal to m omega by 2h cross. This is the same as the alpha that we have evaluated earlier. I was aware of that. That was why I didn't take a different adjustable parameter. Then even equal to, we substitute for alpha in the expression for energy. 3m omega square by 8 into alpha is here. 3h cross square by 2m into alpha is here. Now 8 and 2 cancels, m cancels, omega cancels. Make it, say, 3 by 4 h cross omega. Here also m vanishes, h cross vanish with 1 in the denominator. 3 by 4 h cross omega remains. Make the overall value as 3 by 2 h cross omega. This is also an exact calculation for the first excited state of linear harmonic oscillator. In the beginning lectures, I have told you that for excited state, this accuracy will be limited, but keep in mind that this is a non-problem, a non-system, and I was very clever to take a very suitable and most appropriate trial wave function. Then we replace alpha in the expression for wave function psi1 of x now. Make it say 32 by pi m cube omega cube by 8 h cube. 32 by pi alpha cube was there, alpha is substituted here, raised to 1 by 4 x raised to minus alpha x square. So we obtain the exact format of the wave function within the limits of the variational principle as 4 m cube omega cube by pi h cube, 32 and 8 vanishes, raised to 1 by 4 x e raised to minus half again m omega by h cross into x square. So the principle is very well valid with a very great extent of accuracy for the first excited state as well. If you are interested, you repeat the procedure being applied to the next excited state. Anyway, for the time being, we close with the discussion of linear harmonic oscillator problem here. Now we will move to, if you are interested, you take this as an assignment. The question is, apply variational method to particle in a one-dimensional box problem. It has a Hamiltonian that has only kinetic energy, potential energy is 0. So you will have to consider the physical intuition about the problem. There is one adjustable parameter, that is length of the box. You identify a very suitable wave function that could be x into L minus x. You take it as a x into L minus x and evaluate the ground state energy. Ground state energy is 0. So for ground state there is no wave function. This is actually for first excited state. You evaluate the energy of the particle in a one-dimensional box problem using this trial wave function. Next we will do it for hydrogen atom. That will give you more physical intuition about the very successive problem where we will talk about the variational principle being applied to helium atom. So with that, let me close linear harmonic oscillator problem.